All right, I'll begin. Dear Father, we thank you for this day. I thank you for these students. Pray you to bless our time together. Just help the students as they work on the homework, just to use their time wisely and just to try to learn as much as they can from it. In your name I pray. Amen. All right, so any questions about anything in particular? Someone asked me what fuzzy edges means. I mean, so it goes back to my community college professor. See, because I started in community college when I started college. My dad said if I was going to stay home that I had to go to college. I was like, fine. And then I looked for the degree with the least amount of English possible. And I learned that the electrical wiring degree had just one English course, and I thought, I can do that. And I took a placement test, and they found out I actually had decent math skills. He's like, you should really do electronics. I was like, but electronics has 2 English courses. But he goaded me into it. I was impressionable then. And but in that, he used to forbid us to use fuzzy paper. And what it means is the paper you rip out of like a cheap 3-ring binder. It's got all those, and those things they kind of shed, right? And if you get like 30 papers with these, or just a few of them, when you take them home, you get these little paper shards all over the place. So after his first year or 2 in teaching, his wife forbid the use of fuzzy-edged paper. This is where the term comes from for me. But anyway. Oh, yes, linear algebra. So for this lecture, we're going to let R be a commutative ring with identity. All right? So anytime I say R, I'm talking about a commutative ring with identity. That's really just a shorthand for saying, hey, this R could either be the real numbers, the rational numbers, Z mod n for some choice of n, or something like that. Any of our familiar number systems, it could be any of those things. The constructions I'm talking about today, we could equally well do over any of these choices for numbers, all right? So one of the things I didn't define last time is that if we have A is a m by n matrix, then a transpose is a other way around, n by m. So mami nanu nanu versus nanu nanu mami. And so it's a different size matrix, all right? And in particular, a transpose ij is equal to a ji for all ij. Okay, so the transpose of a matrix gives you a new kind of matrix, which is a different size, but very much related. Basically, it takes your rows and switches them to columns. So if I have A was 1, 2, 3, 4, 5, 6, then a transpose, all right, is actually going to be 1, 2, 3, 4, 5, 6, where I changed the rows to columns. For example, a transpose, the 2, 3 component of it, which one would that be? The second row, that would be not available, right? There's not a third column in the second row, is there? That's not even something I can do. I should do what? How about 3, 2? We could do that, right? Because then that's the third row, the second column. So this is the 3, 2 spot, right? That's equal to 6, which of course is also equal to what? A2, 3, right? So this is transposition. Another example, if I have V is 1, 2, 3, then V transpose is a row vector 1, 2, 3. Okay. What are the properties of transpose? If we have A and B in n by n matrices, and if we have C is a scalar, then if you look at A plus B transpose, it's equal to A transpose plus B transpose. And also, if we have C times A, we're going to be able to prove that that's C times A transpose. So you can pull scalars out. It's additive, all right? So the transpose of the sum is the sum of the transposes. And then there's one other kind of interesting thing. How about if we take the transpose 2 times? Like what's A transpose equal to? A, right? Now, proofs are just about as important as calculations in here, all right? So I assess you on a healthy mix of both of those things. Yep. Yes, thank you. Just as I had planned, just checking to see if you're awake. Of course, intentional. Did I? Oh, just like it was intentional that I waited till everyone late showed up so that I could pass this around. It wasn't that I was just about to forget to take attendance. Hey, I'm curious. Did you guys have classes that are not in the College of Arts and Sciences? Anybody here? Like, you have a class that's not psychology, math, history? Like, do you have an engineering class? Is attendance being taken every day and kept record of in Blackboard? I'm just curious. All right. I digress. Anyway, we talk more about it later. I have my reasons. So, proof. All right. So, I'm sorry. I'll try to focus on the math in here. I'm, as you know, easily distracted at times. Let's prove the first one. A plus B transpose. Now, I would like to look at I'll put another parenthesis around here, ijth element of that. Okay? So that, by definition, is A plus B ji. Okay? What's my next move? Well, we defined the addition of matrices last time, right? And so A plus Bji is Aji plus Bji, right? That's definition of matrix addition. And so then what? Well, that is nothing more than A transpose, parentheses, Ij, plus B transpose, parentheses, Ij. Yep.
Was the transpose intentionally left out in the first step?
What did I write over here? Definition of transpose. What's the definition of transpose? It's that A transpose Ij is Aji. So I'm applying the definition to make that step. Yeah, not a typo. And we're going to have to make that step again. I mean, so if you want to make the transpose disappear, what do you have to do? You flip the indices. And you see I just made a mistake here. Oopsie, that was what? Oh, actually that was fine. Sorry, I apparently shouldn't talk to people and write. Yeah. So again, by the definition of transpose, I switched Ji to Ij, right? Notice that there was a I went from Aji to A transpose Ij. And then finally, the finishing blow, if you will, this is A transpose plus B transpose, big parentheses, Ij. Again, by the definition of matrix addition. And then hence, A plus B transpose Ij is equal to A transpose plus B transpose Ij for all I and j. Therefore, A plus B transpose is A transpose plus B transpose. I don't always have a chance to write that concluding sentence when I'm writing proofs out in class, but it really should be in your solution, all right? I usually say that sentence rather than writing it down. but I do expect you write that sentence down in your proof. But I thought it would be important for me to take 30 seconds to write it down for this proof, just to be clear. Okay? How would we prove the third item? It's almost silly, right? I mean, how do you prove A transpose transpose is A again? If we consider A transpose transpose, parentheses ij, that's what? Yeah, A transpose, put parentheses around it, right? Ji, which is equal to Aij, right? By twice applying definition of transpose. So if we twice apply the definition of transpose, we have that for all ij. Hence, A transpose transpose is equal to A once again. All right. This method I'm using is, the index method, all right, using components and indices to frame arguments. So transpose will stay with us. We have lots more to say about transpose as we go on in here. It's always with us. Oh, one more thing I could say right now. A matrix is said to be symmetric. Here's one important use of the transpose definition. A in R n by n is 1, symmetric if A transpose is equal to A, and 2, antisymmetric if A transpose is equal to minus A. So a lot of times we have homework problems and other theorems and so forth that concern symmetric or antisymmetric matrices. For example, at the end of the course, one of the major theorems we'll look at will be a theorem which says if you have a real symmetric matrix, there exists an orthonormally diagonalizable eigenbasis. That's a very interesting theorem called the spectral theorem, which basically allows you to find nice formulas for quadratic forms and all kinds of things. It has unending applications to engineering and everything else. So symmetric matrices are kind of an important topic. But I don't have anything more to say about it at the moment. All right. So the next order of business is to talk about linear combinations. All right. So what's a linear combination? A finite R-linear combination of, let's say S1, S2, Sn, and suppose these are just elements of some set of objects S, all right? A finite R-linear combination of S1 through Sn is simply C1 S1 plus C2 S2 plus plus Cn Sn. I can write that more concisely as, say, the sum I equals 1 to n of C sub I, S sub I. This is a finite. Why is it an R-linear combination? The one thing I haven't told you yet, I kind of buried the lead here. Why do we say R-linear? Right. What's in the ring R? The S's or the C's? The C's, right. So the coefficients of the sum, these C's, are in the ring. Now, I'm being a little bit vague here. For this to make sense, there must be some way of adding scalar multiples of the object together, all right? In particular, we'll look at this in the context that the set S has things like vectors in it, or matrices, or functions, different objects where we have some notion of multiplying, either by real numbers or complex numbers or some other thing. But this is, generically speaking, what a linear combination is, okay? You could perhaps call it a weighted sum, right? If, a little bit more language here, if C1, C2, all the way on down to Cn are all equal to 0, then it's called, it's the trivial linear combination. Right? Otherwise it's a non-trivial linear combination. And we also say that the set containing 0 is formed by an empty sum. That is, a linear combination of the empty set is just 0. Where that 0 means whatever 0 happens to be in S. If we're talking about vectors, it's the 0 vector. If S is a set of matrices, it's the 0 matrix. If S is a set of functions, it's the 0 function, okay? But this would not be in my notes if it wasn't for the presence of certain very picky students last semester. If you go back for before last year, this escaped my intention. The idea of taking, what is it?
Was that the empty set or 0?
Empty set.
Okay.
Empty set. Empty set, yeah. I feel like we should just leave an extra long space for the empty set, but it would be confusing, right? I don't know. You write something, you get the feeling like it is something, you know? I mean, but I guess it is a thing in terms of set theory. All right, I digress. So linear combinations are such an important part of this course. It'd be hard to find a day in this course where we're not talking about a linear combination somewhere. So let's talk about the standard basis. For Rn. Remember, Rn is my shorthand for the n by 1 matrices. N rows, 1 column, the set of column vectors. So here we have to define EI is an element of Rn where EI, the jth component of it, is just equal to what's called Kronecker delta ij. Delta ij is a combinatorial symbol, and it has the following meaning. It's 1 if I is equal to j, and it's 0 otherwise. That's all it is, if you haven't seen it before. So what this definition says is that the standard basis is such that it's got a 1 in the ith spot, and it's got zeros everywhere else. So let me keep it kind of small here to start with. R2, right? Consider if we have the vector AB, right? I can write that. What? I can write that as A. I can write that as A plus. Well, let me just write down A comma 0 plus 0 comma B. Do you guys agree with that? If you add the vectors on the right-hand side, you get the vector on the left-hand side, right? Because we do addition component-wise. So A plus 0 is A, 0 plus B is B, it matches, yay. And then by definition of scalar multiplication, I can pull the A out, and I can pull the B out. Okay, fine. Here's the in-between step that I just skipped, which is that this is also, what is this? This is A times 1, comma, A times 0, isn't it? And this guy is actually 0 times B. It's going to be B times 0 and B times 1, right? So then by definition of scalar multiplication, I can pull A and B out, and that gives me A times 1, 0, plus B times 0, 1. But by definition, ooh, I'm sorry, I see frowning, and I know why now. Better? Feel better? Yes. I could see Emma was not at peace. Something was wrong. There was a disturbance in the force. Let's see here. I mean, if you believe in that sort of thing, I mean, I don't know. But E1, E2. By definition, that's E1 and E2, okay, for R2. And so what we have then is, what does this show? This actually shows that the vector AB is a linear combination of E1 and E2, right? And which vector is a linear combination of E1 and E2? This is an arbitrary vector, right? So any 2 vector over R can be built from E1 and E2. These are the fundamental building blocks. And there's a theorem that says that Rn is the set of all linear combinations of E1, E2, En. I mean, to be more specific, R linear combinations, right? Essentially, this calculation I just did can just as well be done for Rn. So, you know, if I have, suppose I have the vector v, v1, v2, vn, right? Suppose that's v. So here's essentially the proof. Well, let me not get too carried away. Perhaps this is a proof sketch. I'll put some quotes on this one. I might have a little gap right here. But the gap is mostly just in not doing these details in gory detail for this n1, which probably warrants an induction to be completely pedantic about it. But you can just as well repeat this calculation I did for R2 for Rn and get v1 times 1, 0, 0, v2 times 0, 1, 0, 0, plus vn 0, 1. This is, of course, E1. This is E2, this is En, and in terms of the summation notation, this is precisely the sum I equals 1 to n of V sub I, E sub I. So we can build any n vector as a linear combination of the standard basis. All right? And it also should be somewhat apparent already that that linear combination is unique, right? Like there's no way I can get V from different linear combinations of the E1 through En. If V is 2E1 plus 3E2, it's like there's no way I'm going to be able to say, oh, it's also 5E1 minus 7E2. Like that's not going to happen. The choice of coefficients here, the V's, V1 through Vn, they're uniquely defining the vector V. And likewise, the linear combination. So that's how you build vectors from these standard basis elements. And of course, you know, warning, there's an ambiguity here. Context, right? E1, it's sometimes 1. It's sometimes 1, 0. It's sometimes 1, 0, 0. It's sometimes 1, 0, 0, right? It depends on the context, right? This would be in R, this would be for R2, this would be for R3, and this would be for Rn. So the size of the standard basis element can differ. We use the same notation for all of them because the idea of actually writing the dimension on the standard basis is horrible. Okay. Enough about that. So naturally, if you can do this for vectors, you might wonder, can you do it for matrices, right? So for the standard matrix basis, we define E, I, J, K, L, all right? is equal to Kronecker delta IK Kronecker delta JL. In other words, E ij in R m by n is the matrix which has 0 in every entry, or slot if you like, except the ijth position, or slot, or entry, ijth entry, where we find a 1. But the Kronecker delta formula I wrote for you right there is a very nice, elegant way of saying that. Okay? Again, I'll do a 2-by-2 example just to try to make sure that we're all on the same page here. Suppose I'm looking at the matrix A, B, C, D. All right? By definition of matrix addition and scalar multiplication I gave to you guys last class, we can rewrite this as the sum of 4 things, right? A, 0, 0, 0, plus 0B, 0, 0, plus 0, 0, C, 0, plus 0, 0, 0, D. And then, of course, scalar multiplication, all those zeros are also like 0 is 0 times A, right? So there's an A multiplying every spot there, if you want to look at it. Right? We can look at this as A times 1, right? A times 0, A times 0. I put the cross in just to draw the distinction between the components if I need to. Like if your matrix gets too busy and you want to make sure you can tell which entry is which, just put some lines in, right? They're just decorative. But you see, then I can, by definition of scalar multiplication, I can pull the A out, right? So I could do it here, and I can pull a B out here, and I can pull a C out here, and I can pull a D out here. And what do I have? I have a linear combination of the matrix units, as they're called. So here's E11. This guy is E12. Here you're looking at E21. And finally, last but not least, E22. A 2-by-2 matrix is a linear combination of E11, E12, E21, and E22. These are the fundamental building blocks, which you can build any 2-by-2 matrix from. And they're independent in some sense, right? They're like, there's no way you could get an E12 from the other ones, right? Whatever that independent means. We'll be more precise about that as we go on in here. So, of course, there's a theorem. If A is in Rm by n, then we can write A is equal to the sum I equals 1 to m, the sum j equals 1 to n of a I j e I j. Notice that the aij's are scalars, they're elements of the ring, whereas the eij are matrices. So this gives us a way of tearing apart a matrix into numbers and specific building block matrices, which we use to get it. Now, I'm going to prove this for you guys using index notation, because it's a nice problem to do that. So what we're going to do is we're going to invent a name for this thing right here. Call this thing B for the sake of discussion, all right? And my goal is to show that BKL is equal to AKL. If I can show that for arbitrary K and L, then we got it. So let's look at BKL. That would be the KLth component of this. Now here I'm going to need to use a theorem that I technically speaking haven't proved in here. I mean, we defined addition for two things, right? But in fact, you could use induction to prove that the definition of addition, so let me just write it down over here. Like, you know, I defined in here that a plus b ij was like aij plus bij, right? But you could inductively prove that that extends to if I had a1 plus a2 plus da-da-da plus an, right? Then that would just as well be a1 ij plus a2 ij plus da-da-da-da plus an ij. That's a pretty typical test question, actually. Prove that the definition for matrix addition for two matrices inductively extends to n matrices according to this rule. So if you want to see me do that, come to help session tomorrow. I'll do it. Okay? Yeah. When's the help session? 8:15. Yeah. 8:15. Oh, yeah, 8:15. That's all a certain student's fault for making me teach abstract 2 at 8:15. So once I'm here one day, actually, know what it is? It's that wonderful academic physics lab that I'm teaching. That's what it is. It's here. KL, because that's at 8:15. So we want to show that these things are equal. So we look at the kth component. Now, by the lemma over there that I haven't proved yet, in fact, the kth component of this is just the sum of the kth components in question. So this is actually so we have aij, eij, the kth component of that. But what's the definition of scalar multiplication? The definition of scalar multiplication is that if I have a number times a matrix, and I look at the scalar multiple of it, what is the rule? If I have C times, you know, A, and I calculate the kth component, how does it work? It goes C times AKL, right? So think of this right here as being that constant. And think of the EIJ as playing the role of the A. All right? So by definition of matrix multiplication, of scalar multiplication, this is just the sum I equals 1 to m, sum j equals 1 to n of aij, eij, kl. All right? Now, what's the definition of this? This is what? This is Kronecker delta ik Kronecker delta jl. Now we just have to think about what the Kronecker delta does to the sums. What happens with the sum over j? Kronecker delta jl is only non-zero when what? When j equals to l. So all of those variable j's get lost. All of them are 0, except for the one j equals to l. So this is, in fact, the sum over I equals 1 to m of a, I, l, Kronecker delta, I, k. Just using logic and the definition of the Kronecker delta. Everything's 0 in that sum over j, except for the case j equals to l. And then we use the same argument again. That Kronecker delta ik is 0, except in one specific case. In the case I equals to k, right? So this just leaves me with akl. So check it out. bkl is equal to akl. K and l is arbitrary. That shows that, in fact, yes, any matrix is a linear combination of eij. I don't know about you, but the idea of trying to write that out in this notation is unpleasant, right? Because I would have to write big arbitrary matrices with lots of dot, dot, dots, and then dot, dot, dot worth of those. It's just a mess. This is a much better notation to express such a thing. But I do realize that index notation has a learning curve, which is why I'm spending time on it. You know. If I was unfriendly, I would just say, oh, there's index notation, and then I would put it in homework and never talk about it in class, right? So anyway, so that's that. That brings us to matrix multiplication. So I'll give you a definition. If A is in R m by p and B is in R p by n, then AB is an element of R m by n, where AB ij is equal to the sum k equals 1 to p of A, I, k, B, k, j. So this is the definition of matrix multiplication. Now, admittedly, this seems, I mean, it is pretty much unmotivated. I'm not motivating it at the moment. There is a good motivation for this definition that we'll find a little bit later in the course. But for the moment, I just want to teach you the rudiments of matrix algebra, so I want to just state it and show you how it works. Now, let's see here. Let me just unpack this definition a little bit for you. It's useful to rewrite it as a dot product. You guys know what dot products are? Well, let me just kind of find our way to that. This is, another way we could look at this would be the sum k equals 1 to p of rho I of A, the kth component of that. See, that's the kth component of rho I by the notation we introduced in the first class, right? And this guy, well, that's the kth component of the jth column. Notice that the j and the k flip around for the column, whereas they stay in the same order for the row. If you're uncertain, think about it. Write down the matrix that we wrote down last time and look at them. Okay? Then this thing right here, where you take the kth component of rho I and multiply it by the kth component of rho j, and you add those up going from k to p, this is called the dot product of the ith row of A and the jth row of B. This is exactly what we mean by dot product. We write a dot. And it's just for the sake of not being overly pedantic, I'll allow us to take dot products of rows and columns as long as they have the same size. Okay. So going from here to here is just a definition. Here's an example of a dot product. If I have 1, 2, 3 dotted with 4, 5, 6, what do I get? Some of you have had calculus 3, so you're like, really? For those of you who have not had calculus 3, you're like, ah! What's happening? Why? This is why I say calculus 3 is sometimes helpful, but not that much, really. I mean, geometrically, yeah, 28, 32. So the dot product of two vectors is a number, okay? There are all kinds of fascinating geometry as to what that dot product really means. But anyway, that's a dot product. Oh, also, there's special cases here. What would this mean if m and n are both 1? Then is there any index then? There wouldn't be, I mean, there's no, we don't put indices on just one-dimensional things, right? I tell you x equals to 5, and then I say, what's the first component of x? And you're like, it's 5. No one says that, right? I mean, okay, so anyway, my point is that the I and j disappear in the case that m and n are both 1. That's a special case. Hey, let me talk about that special case just briefly. Let me just be less mystical about it. If we have A is in R1 by P, and B is an element of R P by 1, what's that mean? A looks like what? A row vector, right? And a column vector, right, for B? So the matrix multiplication is just the dot product in this case. So there's no extra ij floating about. Okay. I keep thinking we have to 1, but that is wrong, right? Then again, this phone is unhelpful. When I look at the outside thing, the 1 looks like a 7. So, but actually it's 12:41, so we're okay. So we got some time. Actually, it doesn't really matter where I get to today because we're not going to finish matrix multiplication at the moment. There's just no way. So I'll do some examples. Think that'd be good. So if I have, let's say 1, 2, 3, 4, 5, 6. It seems like all of my matrices are the same, doesn't it? So if I take this and I multiply by the column vector, 0, 1, 0, I could do that. All right. The definition of matrix multiplication says that I get a what? This is a 2 by 3, and I'm multiplying it by a 3 by 1. So what I should get over here is a 2 by 1. Yeah. And in particular, I get 1, 2, 3 dotted with 0, 1, 0, and 4, 5, 6 dotted with 0, 1, 0. So that's just what? Two and 5. So I get 0 times 1 plus 2 times 1 plus 0 times 3, which is 2. I've got 4 times 0 plus 5 times 1 plus 6 times 0, which is again 5. Let's see here. How about, what if we look at 1, 2, 3, 4 times 0, 1, 2, 3. How's this going to work? Well, we have 0. Well, I'll write it out again. I will, at some point, stop writing these, of course, and just do it. But since we're starting, there we go. Now here's how I visualize it. I think like 02.12, 02.34 for that one. So I think actually that taking my hand going like that, junk, ka-junk, like that, and that gives me this over here, and so forth. I don't know. I found this helpful as a student, but and what do we get? We get 4 This works out to 8. That's 1 plus 6, which is 7. And this is 3 plus 12, which is 15. Okay, so let's call this A. Let's call this B. Let's calculate BA. What do we get for BA? So I'm just going to do it in my head this time. That's 3. And then I usually do the first column first. Then 2 plus 9 is 11. Already, you can see that AB is not equal to BA, right? If they differ in even one component, they're not equal. You can see already that the the 1, 1 components don't match, right? Let's see here. We get 4. We get 2 times 2 is 4, plus 12, which is 16, right? So this illustrates a general phenomena, which is that matrix multiplication does not commute, right? A times B is not equal to B times A. You have to be really careful about this for symbolic problems. Be careful not to assume that matrices commute. If you do, you'd be wrong, usually. Okay, my third example is a little bit more interesting. What if we take E, ij, right, and we multiply it by, let me be a little bit less adventurous. What if we take A times EI? What's this equal to? Oh, I guess I actually do need to know that let's say EKL times EI, what's that going to be equal to? Suppose that, this makes sense. So this is an m by n, so this better be n by 1. If I calculate the what kind of thing am I looking at here? Altogether, I'm looking at an m by 1. This is another special case of the definition, right? I talked about what happens if both m and n are 1, but there are 2 other cases to think about in terms of the index appearing differently, right? If just one of them is 1 and the other one is not 1, or vice versa, that will either give you a row or a column vector as the output. In this case, we have a column vector. So the definition of matrix multiplication here is a little bit different. We just say a letter I haven't used yet, let's say J. And so this should be the sum. I guess I'm supposed to do P equals 1 to n. Trying to be careful not to reuse a letter in a different sense. EKL. All right. So the EIJ is playing the role. So which one of these indices is not present for a column vector? The row index or the column index? The column index is gone. So the I is still there, and that I in this is being played by J. So I'm like J, P, and then E, I, the pth component of that. Now, it's just a mess of Kronecker deltas, okay? So this is the sum P equals 1 to n of Kronecker delta Kj, Kronecker delta Lp, Kronecker delta, so many Kronecker deltas, Kronecker delta Ip. Goodness gracious. What does that simplify to? The P is a dummy variable of summation, so that should be gone. But the I, the K, and the L, and the J, these are free but arbitrary indices which are describing what we're doing. So the P goes away, and we put P equal to I, basically. So this is just Kronecker delta Kj, Kronecker delta Li. But what's that? That is exactly the, let's see here, we could also write that as Kronecker delta Li Ek, the jth component of that. So in short, I have shown that if we take EKL and we multiply it by EI, what we get is we get Kronecker delta Li EK. Yeah.
Why did you do Li and not IL? Because the order of the Kronecker delta.
Why did it do IL and not L?
Or
Where?
Li, not IL.
Where?
Third, the sum of p equals 1. The third.
Oh, you're saying that should be, logically, that should be.
Well, no, I'm saying why didn't you do one way or the other?
Oh, have I done it in different order than I did before today?
No, I don't know. So I'm asking.
I think I've maintained the order, but actually you're right, it wouldn't matter because the Kronecker delta is symmetric.
Okay.
So, like Kronecker delta ij is equal to Kronecker delta ji, so forgetting which goes where actually won't hurt you in that regard.
Okay.
Now, anyway, if I had more time, I'll do it tomorrow, since I guess I'm what I was getting to, and I'm out of time, so I won't do it. But we can prove, in fact, that AEI is equal to the ith column of A. So multiplication on the right of a matrix by the ith standard basis selects the ith column. I actually showed that to you already in my example back over here. See, I took A times E2, and this is column 2 of A. I need to do a little work on the interrelation between the matrix units and the standard basis to derive a few things about multiplying these. So anyway, next time we'll do that, and hopefully we'll introduce the concept of an inverse matrix. And I'm thinking by the end of next class we'll actually have talked about equations a little bit. So, thanks guys. You are free to ask questions in the help session that are ahead of lecture if you want, by the way. So if you're like working on your homework and you have a question about something that I haven't gotten to lecture-wise, if time permits in the help session, I'm willing to talk about stuff I haven't gotten to yet in lecture. For example, if you wanted me to show you an example of Gaussian elimination tomorrow, I'd be happy to do it.